Hi everyone, my name is Salvy Bourguet. I'm coming from the University of Nantes and I work for the IRENA lab in Saint-Nazaire in France. And I will present you my part on the electrotechnical architecture of wind farms and the design based on CAPEX and reliability KPIs. As an introduction, we can see here the three main configurations we address with this work. The objective is to optimize the MV, medium voltage and high voltage architectures, like the HVAC and HVDC links from the shore to the offshore site, and also the MVAC and MVDC distribution network inside, that is here for the meshing of the turbines inside the site. These approaches are made with a technical and economical aspects, and we look at the losses and try to minimize them, and also with regards to the CAPEX and OPEX performances of the configurations we obtain. And all those calculations are made with the external constraints, and such as site topology, and also look on the wake effect and the reliability issues, which I will present you during this presentation. Now, on this side, you can see that the objective is quite clear. It's the minimization of the losses, so maximization of the energy we can supply to the network, and also to minimize the investment. That's the trade-off between those two parts that we are looking at. The problems variables are the generators meshing, so the distribution network inside, the MV and HV cable sections that could be variable per segment and such distributions, and the positions and the number of the substations and their architecture also, and for AC systems, the reactive power compensation. The input data are often fixed by some hydrodynamics studies, like the characteristics of the generators in numbers and positions and productions level. But also we can choose or let the algorithm choose itself the MV and HV types, type A, DC or AC, and the levels for the voltages. The input data is also given for the offshore substations consumptions. As we can see here, we have different steps in this algorithm, in this approach, in this work, and we especially start with the sizing power components and look at the different stages with the different steps: construction of the MV collection network layout for the first step, placement of the substations for the second one, and the construction of the HV transmission network layout for the third one. This helps us to compute the LCOE based on the CAPEX, OPEX, and AED calculations. As we can see here, as a more complete presentation, we have the available modules in our simulations, in our platform, with the considered inputs as wind resource database, or general inputs considering the turbines and the components database. We're able to take into account several elements like the wake effect or the reliability of the configuration you obtain, and of course a load flow calculation for the electrical losses and performances. All this algorithm is built in the goal to produce the wind farm optimization based on several aspects, objectives that we can discuss later. To remind you, as the general global diagram of the optimization process, it's often the same case. The optimization algorithm tries to generate a situation, which in this case is an architecture for the general system. We evaluate the performances of the electrical network and obtain at least the losses and the investment performances. And this is a circle like generation and evaluation, and it tries to converge to the best situation for mono objectives or to the best Pareto front for the multi-objective studies. And inside, the methodology is as follows. We have two different algorithms that are coupled. The first one is based on the geometric algorithm. Its goal is to generate the turbines into groups. As you know, we have several groups, and they are not meshed at this stage. And the meshing is done by the Prim's algorithm, which makes the links inside the groups with a minimum spanning tree approach, like you have on the right here. So it lets us obtain radial meshed stars and so on. All the configurations can be obtained with those two algorithms, and it converges quite quick compared to the genetic algorithm itself only. Considering the losses and the investment, we can have a look for in AC and DC systems. We have a load flow calculation for all the systems, and also for coupled AC and DC, which means we can study hybrid situations with the HVDC and AC systems inside the farm. These are looked with regards to the investment parts on NV and HV submarine cables, and the different costs we have here are variable with regards to the sections or lengths depending on the technology. We also have a module for the offshore substation based on several models for the transformers, protections, and platform, varying with a regard with the power or number of cells and so on. That's the same for the compensations. In this one, we can have a look at some case study as we've done it on the Salvy offshore wind farm, which is ongoing right now. Just a quick presentation. It's a 480 megawatts farm with 80 turbines, which will be 6 megawatts each, and the distance between the turbines is around 1 kilometer. There is only one offshore substation based on 33 to 225 kilovolts, and the link to the shore is done with the 2 cables on HVAC technology. The design park shows 14 groups of wind turbines in chain. If we focus on this one, the estimation of the production is about 1,700 gigawatt hour per year, and the equivalent availability factor is about 40%, with a mean wind speed on the site of 8.5 meters per second. If we switch to what we obtain with the optimization process, if we look at the different results we can see here in the frame of mean losses on the x-axis and total investment on the y-axis, we can see a comparison of the optimization results in this optimization space. For instance, if you look to the blue points, the blue points represent the reference architecture with different assumptions on fixed sections of the cable or cluster, fixed sections or variable sections. If you can see, those 3 points are moving in the space, but they are defining what we can expect from this architecture for now. As a first look, we can look at the red squares. The different red squares correspond to different assumptions, but for mono-objective calculations. And it seems that they are quite an improvement in the total investment and also in the losses, depending on the assumptions we made. And the last part is the red triangles. If you look, it's Pareto front obtained with a multi-objective calculation, and it lets us explore a larger zone with this optimization process as usual. And we can also see that several configurations can be discussed thanks to this optimization tool. If we go a bit further, we can have a look at the reliability impact of such architectures. I present you on this slide the different steps we have in our study. The first one is beginning with the electrical design on the top left of this slide. As you can see, it's a small example with 8 turbines. And in this architecture, we have a second step which translates this electrical architecture to a reliability diagram, which is composed of different nodes, the perfect ones, the wind turbines as sources, and the cable links. And each of those elements are regarded as a new element, and it is really easy now to use this, because there is no more electrical calculation and so on. So it's just a graph, and the graph calculations are really fast and accurate. The third step here is to look for each source, how it could supply the first node, how it could deliver its production. So it's an approach where we look for the minimum path research, which means what are the ways that could follow the energy or the power to go from one source to the number one. And then with such paths research, we can express the performance of the reliability performance of this situation based on the fourth step, which is based on the components data. And the components data are two data. It's outage frequency, lambda, which express the number of outage you can have per year, and the mean time to repair for each of them in hours per occurrence. Based on those approaches and the different nodes we can encounter for the power flow, let's say, we can express several indexes like the ENS, AOH, or EAF. For instance, ENS is the expected energy not supplied, which considers how much energy you won't supply due to outages in your architecture. The second one, the annual outage hours, corresponds to a number of hours within outage for your site, as it is normalized by the total hours of production per year. And the equivalent availability factor, which is really well known as a percentage of the nominal power you can produce during the life of your system, considering all the outages you have in the different systems. And of course, we also have a look to the investment part in euros mainly. Then for this Saint-Nazaire Park, you can see here 4 different results. Let's start for the first one on the top left. It's the reference architecture. In this reference architecture, if we look at the 3 different values, we have an investment of 260 million euros. And for this situation, as it is designed today, we have only one substation and radial configuration. This situation gives the ENS of 100 or nearly 200 gigawatt hours per year. And this is including a cost with the ENS. It means with the energy not supplied into the calculation of about 938 million euros. If you go to the second configuration on the top right, we have an optimization based only on the investment part, which is here minimized as 242 million euros. But as you can see, by doing this, you obtain a situation quite different with 2 substations, 2 links, and again, a radial configuration. But if you look at the other performances on the ENS and the cost, this has increased largely, and it's a too large increasing considering this only on the investment part. So one question could be to look at an optimization based on different elements, and that is the case for the 2 cases on the bottom left and right. If you look at the left and the right, you can see that in those 2 configurations we obtain no more radial configurations, but meshed configurations, and 1 substation on the left and 2 substations on the right. But for those 2, we only have 1 link for the onshore. If we look at the different performances, they are quite close, but they have an increase in the investment for all of them. But the ENS is very low, and the cost including the ENS is really low too. So it means that the optimization considering this park, if you include the investment and the ENS calculation, makes a good situation and something that is quite new in the optimization processes. Now, if we have a look at the wake effects, we can have a quick look at a case study from the France Énergie Marine Valloret project. It's a given test case with 40 turbines layout, as you can see on the left. And there is an exclusion zone between these, the third and the fourth row. Here we have 40 turbines with about nominal power of 8 megawatts, and the distance is 5D for the y-axis and 8Ds for the x-axis. We use here the wind characteristics of the Bourguet site, which is something really well documented, with a mean wind speed of 9.3 meters per second and a quite strongly oriented wind rose on the southwest part, as you can see here. If we have a look inside, we can say that the effects of the wind repartition could be quite strong. Here you have a figure for the 14 meters per second case, and you can see on the x-axis you have the number of the turbine from the previous figure, and the y-axis represents the direction of the wind, where it's coming from. And we can see that in some wind directions, they are heavily affected. So, for instance, at 14 meters per second on this figure, we can see the attenuation can reach about 15%. And if we go to 4 meters per second, for instance, the attenuation can reach 50% with the Jensen model of the wake effect. But at this stage, it doesn't really represent the final production, so it must be correlated with the effective production and modulated by the wind rose of the site. But that's the first step. Now, here we can look at the effects on the production. So that's the same figure with the numbers of turbine on the x-axis and the wind direction, the y-axis. And we can see a lower influence due to the production curve. Several wind directions are critical, by the way, and it is linked to the park's configuration. For this application, we could have guessed that directions could be 0 and 180 degrees. But here, for this figure, at 14 meters per second, the production can be lowered by about 1 megawatt on several turbines, depending on the wind direction, which represents something that is really important. If we look a bit inside again, we can see that if we have the global efficiency of this park, the global efficiency is about 41.8% for this configuration. But if we look inside, considering the weight effects, we have different situations, and we have variations of this efficiency from 38.5% for one given turbine to 45.6% for the external turbines of these configurations, which means that certain zones are more sensitive to this wake effect, and it is also something that we look at for the redundancy positioning if we need some in this configuration. And it is also, of course, linked to the park configuration. So this study can lead the choices with regards to the wind rose, the park orientation, and the technology we finally install inside. So as a conclusion, I can say that our work focuses mainly on the obtaining the best configurations for the wind farms or the tidal farms. It works also for such elements. And since the maturity level is not the same for all technologies, the reliability is a key factor for offshore development. And we can see in small studies that it has a strong impact. And of course, the definition of the objectives and the expected performances is compulsory and drives the study and the results. Well, on such an approach, we have some limitations due to the huge number of parameters we take into account. And we can also always ask ourselves if the global optimization tool exists and if it's reliable. But it helps people to choose between different situations and maybe to observe the performances that are quite hard to calculate or to obtain by hand. One of the other limitations is the integration of the industrialization processes constraints, and maybe to be able to calculate the use of today and tomorrow for such a site. And well, thank you. That's all for today.